In this video, we're going to look at problems involving dimension analysis. And the first question is saying, for any equation to be valid, it must be homogeneous. Explain what is meant by the term homogeneous. So, homogeneous is actually when an equation is dimensionally correct. And an equation is dimensionally correct if the dimensions of various terms on both sides of the equation are the same. So, if we end up having the same dimension at the left side of the equation and at the right side of the equation, and that dimension is raised to the same power, then we will say the equation is homogeneous or it is dimensionally correct. Let's look at the next question. The next question is saying that show that the following equation are homogeneous. So we have to show if this equation have the same dimension on both sides of the equation or not. So we have the first equation, which is s is equal to ut plus half at squared. So this equation falls under the equations of motion. So we first have to identify the quantities that are in this equation. So we have s, which is displacement, u, which is velocity, t, which is time, a, which is acceleration, and t, which is time. So after identifying these quantities, we're now going to write the SI units of these quantities. So we have the quantity displacement, which falls under length, and length has the SI unit meter, is equal to velocity has the SI unit meter per second, time has the SI unit second, plus 1 over 2, acceleration has the SI unit meter per second squared, multiplied with time has the SI unit s. Since t is squared, we're also going to square s here. Now we're going to write this part and this part in form of a fraction. So meter is equal to meter over second times second plus 1 over 2 meter over second squared times second squared. And now on this step, now we're going to write the dimensions instead of the SI unit. So meter has the dimension L, because meter is the SI unit for length and length has the dimension L. Meter, its dimension, it's L, over second, which is the SI unit for time, and time has the dimension T. So we're going to write T. Same applies here. For this S, we're also going to write T plus 1 over 2. Meter is the SI unit for length, and length has the dimension L, over second for time, and time has the dimension T. Since second is squared, T is also going to be squared. Same applies here. We're going to have T squared. If we have the same thing at the denominator and the same thing at the numerator, we're going to cancel them out. So we'll have t here, they cancel. T squared here, they cancel. And we're going to remain with L is equal to L plus 1 over 2 L. So we're now going to add this. So we have L is equal to L plus L over 2. L is equal to, so we're going to drop 1 here. So L is equal to, the common denominator here is 2. So 1 into 2, that's 2. 2 times L, that's going to give us 2L, plus 2 into 2, that's 1. 1 times L, that's L. L is equal to 3L over 2. So L is equal to 3 over 2 L. So does this equation have the same dimension on the left side of the equation and on the right side of the equation? So an equation is homogeneous if the left side of the equation and the right side of the equation have the same dimension, and if that dimension is raised to the same power. So we have L at this side of the equation and L at this side of the equation, which is the same dimension. And this L is raised to the power 1, and this L is also raised to the power 1. So meaning this equation given is dimensionally correct. And this number here, 3 over 2, it is just a constant number. It has nothing to do with an equation being dimensionally correct or not. let's look at the next equation, which is PE is equal to KE. So does this equation have the same dimension on both sides? So potential energy is mgh, which is equal to kinetic energy is half mv squared. So let us identify the quantities in this equation. So we have mass here, m is for mass. We have g, which is acceleration due to gravity, so this is just acceleration. And we have h for height, and we have m here for mass again, and v for velocity. So after identifying these quantities, we're going to write the SI units for these quantities. So the SI unit for the quantity mass is what? Is kilogram, multiplied with the SI unit for acceleration is what? Is meter per second squared. The SI unit for height, which falls under length, is what? Is meter, is equal to half. The SI unit for mass is what? Is kilogram, times the SI unit for velocity is what? Is meter per second. But since V here is squared, I'm also going to square this. Now I'm going to distribute the two. So we have kg multiplied with m per second squared multiplied with m is equal to half kg multiplied with m squared per s squared. So now I'm going to write this and this part here in form of a fraction. So I'm going to have kg multiplied with m over s squared multiplied with m is equal to 1 over 2 kg multiplied with m squared over s squared. So I'm going to multiply this because they are like terms. So kg multiplied with m times m is going to give us what? M squared over s squared is equal to 1 over 2 kg multiplied with m squared over s squared. Now at this stage, I'm going to write the dimensions instead of the SI unit. So kg here is the SI unit for mass, and the dimension for mass is m, multiplied with meter is the SI unit for length, and the dimension for length is L. Since meter is squared, I'm also going to square L, over S here is the SI unit for time, and the dimension for time is T. Since S is squared, I'm also going to square T, is equal to 1 over 2. kg is the SI unit for mass, and the dimension for mass is M, multiplied with m here is the SI unit for length, and length has the dimension L, and since m is squared, I'm also going to square L. S here is the SI unit for time, and the dimension for time is T. Since S is squared, I'm also going to square T. So now I'm going to write this T at the numerator and this T at the numerator, and we know if we're writing something that was on the denominator at the numerator, we actually multiply the power with the negative. So I'm going to have m multiplied with L to the power 2 multiplied with T. This 2 I'm going to multiply it with a negative, and it's going to give me a negative 2 is equal to 1 over 2 m times L to the power 2 T to the power minus 2. So is this equation dimensionally correct? Does this equation have the same dimension on both sides? So we have the dimension m here, dimension m here, dimension L squared here, dimension L squared here, dimension T here, dimension T here, and m here is raised to the power 1, m here is raised to the power 1, L here is raised to the power 2, L here is raised to the power 2, T here is raised to the power minus 2, T here is raised to the power minus 2. So this equation is dimensionally correct. This 1 over 2 has nothing to do with an equation being dimensionally correct or not. So this 2 is actually a constant number.